The James Webb Space Telescope has just uncovered galaxies that should not exist, mature spirals, heavy elements like platinum, and even supermassive black holes forming only a few 100 million years after the Big Bang.
NASA unveiled pictures from a new space telescope capturing the deepest images of the universe anyone has ever seen.
None of this fits our current models of cosmic evolution. Did black holes build galaxies instead of destroying them? Are we seeing cracks in the very laws of physics or evidence of an unknown cosmic architecture shaping reality itself? Stay tuned, because what Webb is showing us may rewrite the history of the universe. The deeper the James Webb Space Telescope delved into the early universe, the more it unveiled a domain that seemed alien, not merely in terms of distance or scale, but in the very logic that governed it. Following the initial impossible encounter with the mature, structured galaxy from the cosmic dawn, the telescope began to observe peculiarities that expanded far beyond isolated anomalies. These weren't just outliers against the backdrop of accepted theory. They formed a constellation of contradictions that collectively pointed to an entirely unrecognized layer of cosmological architecture. New targets selected to investigate the same epoch as the original discovery began yielding results that were progressively more unexplainable. For instance, several galaxies exhibited not just chemical richness but compositional anomalies. These were ratios of elements that defied known stellar nucleosynthesis patterns. Instead of the expected proportions dominated by hydrogen and helium, there were galaxies with abundant signatures of elements like magnesium, silicon, and even platinum. These were not just present in trace amounts. In some cases, they appeared in concentrations suggestive of intense stellar recycling cycles. But such cycles required time that simply hadn't passed yet. This pointed to a hidden mechanism, perhaps a hyper-efficient stellar generation system, or even a non-stellar origin of heavy elements. Among Webb's deep-field surprises was a pint-sized spiral galaxy only a few thousand light-years across, yet perfectly formed. Its low metallicity stars twinkle blue, meaning the gas remains nearly pristine, untainted by heavy elements from earlier generations. Despite its youth, delicate arms swirled gracefully around a compact core, challenging ideas that spirals require maturity in metals to settle into order. Webb's view of this tiny, orderly disk inside a rough cosmic neighborhood suggests that some galaxies learn to dance elegantly long before the music of cosmic evolution finishes playing. Deep surveys with Webb's NIRSpec have turned up what scientists are calling firefly galaxies. These are compact, red, and dazzlingly dusty objects existing just 300 million years after the Big Bang. One record-setter gleams brighter than many mature spirals, yet its light is reddened by heavy elements and carbon-rich soot thought impossible so soon. Supernovae must have exploded rapidly, forging dust and metals in frantic waves that cloak newborn stars. These findings upend timelines, showing that cosmic chemical factories switched on almost immediately, lighting the early night with surprisingly complex, shimmering fireflies. And at the heart of these contradictions, an even stranger suspect began to emerge, black holes appearing far sooner and playing roles far larger than theory ever allowed. The role of black holes in this narrative became more central as Webb continued its observations. Supermassive black holes and quasars were appearing impossibly early in cosmic history. A new hypothesis emerged suggesting that early black holes may have functioned not just as galactic anchors but as cosmological accelerators. These were regions where matter, energy, and even information could be compressed and transformed in ways yet to be modeled. If some primordial black holes had properties beyond those currently known, if they could spawn stars, seed galaxies, or even generate localized expansions of space, they might be the architects of these impossibly early galaxies. Cross-disciplinary collaboration erupted as scientists grappled with these findings. Quantum physicists, data scientists, and philosophers of science found common ground in the need to interpret a universe that no longer conformed to linear extrapolations of the past. Artificial intelligence tools were employed to sift through terabytes of observational data, looking for hidden correlations between anomalies. Machine learning algorithms began detecting subtle patterns that hinted at a deeper cosmic structure, a fractal rhythm, or an underlying symphony of form and energy playing out over scales far beyond human comprehension. In Webb's Sears mosaic, galaxy Sears 1019 hosts a black hole 9 million times the Sun's mass, while the universe was only 570 million years old. The quasar roars so brightly that it outshines its modest host, challenging ideas that such giants need cosmic ages to grow. Spectra reveal furious star birth alongside gas sprinting at thousands of kilometers per second, evidence that the black hole both feeds and blasts its surroundings. Did black holes form first, building galaxies around them? The existence of this early monster forces theorists to rewrite the timeline of cosmic evolution. This is just the beginning of our journey into Webb's impossible discoveries. The chemical and structural mysteries we're uncovering challenge our most fundamental assumptions about how the universe developed. What we're seeing suggests that the early cosmos was far more active and organized than we ever imagined possible. But the real shock came when Webb revealed that these extraordinary galaxies were not rare exceptions, but part of a much larger cosmic pattern. If you like this video, be sure to subscribe and hit the bell so you don't miss any future episodes. Don't forget to share it with your friends too. It helps the channel out, and I'm excited to continue bringing you more awesome content. The mystery grew deeper when Webb's follow-up observations revealed that this was far from an isolated case. Across the same early epoch, more galaxies appeared that were unexpectedly massive, luminous, and intricately organized. Among the most striking features was their light signature. Instead of the anticipated glow of pristine hydrogen and helium, the ingredients expected from the first stars, Webb's spectrograph detected fingerprints of heavier elements such as carbon, oxygen, and even traces of iron. These elements are normally forged in the cores of stars and dispersed by supernovae. For them to appear in such abundance, several generations of stars must have already lived and ended their cycles. Yet, within this narrow window of cosmic history, that sequence of events should not have been possible, hinting at either an astonishingly accelerated process or an entirely different mechanism of element creation. Equally fascinating was the galaxy's refined structure. Their spiral arms did not resemble the chaotic patterns expected from such a young universe. Instead, they appeared elegantly wound around luminous centers. Such an order required not only time but also gravitational balance and long-term interactions. How could such harmony emerge so quickly in a universe still in its infancy? One possibility was that black holes had formed astonishingly early, anchoring galaxies and shaping their evolution at a pace far beyond current models. The implications were profound. If galaxies like these were already flourishing, it meant the universe's building blocks, dust, heavy elements, and stable star systems were established far earlier than anticipated. This suggested that stellar nucleosynthesis might have unfolded in ways beyond present understanding. Perhaps the first stars burned faster and died sooner than models predict. Or perhaps an unknown process enriched the cosmos with remarkable efficiency. Either way, the timeline of cosmic evolution seemed in need of revision. This prompted scientists to explore bold possibilities. Could dark matter have played a more dynamic role in shaping the early cosmos? Might our interpretation of redshift, the measure of distance and time, require revaluation? Or could these discoveries hint at entirely new physics, perhaps a modification of gravity itself, or even interactions with parallel universes subtly influencing our own? As scientists explored the galaxy's motion and gravitational lensing effects more closely, fresh puzzles began to emerge. The gravitational field enveloping this system was far stronger than its visible mass alone could explain. Typically, such a discrepancy is attributed to dark matter, the invisible framework thought to hold galaxies together. Yet in this case, the gravitational influence appeared far more concentrated and orderly than the diffuse, cloud-like halos usually observed around galaxies today. This raised intriguing questions. Could we be witnessing a new kind of gravitational interaction, an unfamiliar state of matter, or even a variation of gravity itself that only reveals its nature under certain cosmic conditions? Adding to the mystery was the galaxy's striking isolation. In the early universe, galaxies usually gathered in clusters or proto-superclusters, their growth shaped by shared gravitational fields and cosmic filaments. Here, however, the galaxy appeared to stand alone, detached from the familiar web of galactic companions. The surrounding space was unusually pristine for such an early epoch, with no telltale signs of collisions, no disrupted arms, no faint stellar trails. This surprising solitude hinted at either a radically different path of formation or a protective mechanism that shielded the system from the universe's turbulent interactions. The very existence of such an organized, independent structure suggested that the architecture of the cosmos may be far more diverse and dynamic than once believed. These unexpected traits push scientists to re-examine older observations, searching for overlooked clues that might reveal just how long such mysteries have been with us. In the aftermath of this discovery, theorists began revisiting older satellite archives, asking whether instruments such as Hubble or Spitzer might have recorded similar objects without recognition. Their sensitivity to infrared light was limited, which meant that subtle signals could easily have slipped past unnoticed. Retrospective analyses of faint anomalies and ambiguous data revealed intriguing hints, whispers of galaxies that may have appeared before, too faint to stand out clearly, and often dismissed as background noise or set aside because they did not fit prevailing models. This raised the exciting possibility that such galaxies were not new to Webb alone, but had been quietly present in the data all along, hidden in plain sight by the filters of our expectations. Even more captivating was the galaxy's potential link to the nature of time itself. Some models began to explore the idea that time may not flow uniformly across the universe, but instead might vary depending on the local energy density of space. From this perspective, cosmic time bubbles could exist, regions where time expands or contracts at different rates, shaped by space-time curvature in ways still not fully understood. Within such a bubble, a galaxy could evolve at a steady pace while appearing, from our vantage point, to develop impossibly quickly. Far from breaking the rules, this framework would suggest a new layer to the interplay between quantum mechanics, relativity, and cosmology. Another bold avenue of interpretation drew from the holographic principle, the proposal that our universe may be a three-dimensional projection of information encoded on a distant two-dimensional boundary. If this concept holds, then the distant galaxy might not be a thing in the traditional sense at all, but rather a manifestation of deeper informational structures, a visible expression of the universe's underlying code. From this angle, Webb's detection could be seen not just as a glimpse of an ancient galaxy, but as a rare encounter with the architecture of reality itself. A clue pointing toward the profound connections between physics, information, and existence. While these theories pushed the boundaries of physics, Webb was simultaneously uncovering clues about life's chemical origins hidden in the coldest corners of space. Deep within the chameleon molecular cloud, Webb's spectrographs traced the coldest dust lanes ever studied, revealing a frozen reservoir of life's essential ingredients. On tiny grains of dust, the telescope detected water, carbon dioxide, methane, ammonia, and even methanol, molecules that play vital roles in prebiotic chemistry. Locked away at temperatures near minus 250 degrees Celsius, these ices are destined to ride aboard comets, eventually seeding young planets with the raw materials for complex chemistry. This survey represents the most comprehensive inventory of solid-state molecules ever conducted in space, showing that the blueprint for life begins forming in cosmic shadows long before stars ignite. From there, Webb turned its gaze outward, probing a distant region bathed in the faint afterglow of the early universe. The light it captured had traveled for billions of years, originating not long after the Big Bang. With its infrared vision, Webb was expected to uncover small, turbulent galaxies just starting to assemble, the first chaotic attempts at structure in a young cosmos. Yet the observations told a different story. Instead of fragile, newly forming systems, the telescope revealed a massive, fully developed galaxy with spiral arms and a luminous, ordered core. Such complexity was thought to require billions of years of cosmic evolution, and yet this galaxy already existed when the universe was less than 400 million years old. Adding to the puzzle were subtle background fluctuations in regions empty of galaxies. These faint energy signatures were too structured to be dismissed as random noise, yet too irregular to match known forms of matter or radiation. Their patterns loosely aligned with theoretical predictions of decaying vacuum energy or remnants of false vacuum states left over from cosmic inflation. If borne out, this would suggest that the universe may still be transitioning between energy states, gradually settling into the physical laws we observe today. A further layer of intrigue came from polarization studies. Webb's polarimetry instruments, designed to measure the orientation of light waves, revealed unusual twists in the polarized light from some galaxies. These signatures did not align with the effects of dust scattering or magnetic fields. Instead, they hinted at interactions with chiral particles, particles whose behavior depends on their orientation. This raised the possibility of an early universe preference for handedness, a symmetry bias that could help explain why matter dominates over antimatter. If such interactions shaped the early cosmos, their influence may have cascaded through galaxy formation, stellar birth, and even the conditions that make life possible. The Webb telescope's extraordinary precision opened a new window onto this galaxy, allowing astronomers to study it with a level of clarity never achieved before. Its resolution was so sharp that individual star-forming regions could be identified, while streams of gas winding through its spiral arms were carefully traced. These observations revealed not only the details of a single unusual galaxy, but also a vision of the early universe that appeared more mature, dynamic, and structured than standard cosmological models had ever suggested. It was as though Webb had tuned into an alternate version of cosmic history, unveiling patterns of evolution far earlier than expected. What made this discovery even more compelling was its growing statistical weight. A solitary case might have been dismissed as an outlier, but Webb continued to uncover more ancient galaxies displaying similar levels of advancement. With each new detection, the evidence pointed toward an overlooked chapter in the universe's story, one in which complexity emerged far sooner than once believed. The JADE survey then pushed the boundaries of cosmic exploration to galaxy JADE's GSZ 14-0, shining a mere 290 million years after the Big Bang. Webb's spectrograph confirmed its record-breaking redshift of 14.3, establishing its extreme distance. Yet distance was only part of the surprise. The galaxy glowed brightly and carried signatures of oxygen, signaling that rapid cycles of star formation and supernova explosions had already enriched its environment at a time once thought chemically barren. Though its compact core spans just 1,600 light-years, it radiates with the brilliance of billions of suns, challenging long-held assumptions about how quickly the first galaxies ignited. Another remarkable case came from JADE's GSZ 13-0, observed 330 million years after the Big Bang. This galaxy emitted strong Lyman alpha radiation, light that should have been absorbed by the sea of neutral hydrogen still filling the cosmos. Instead, its ultraviolet output had carved a vast bubble of ionized gas, clearing a channel through which its photons could escape. This discovery provided a direct clue to the epoch of reionization, showing that the process unfolded in patches and far faster than anticipated. Small but powerful galaxies may have pierced the cosmic darkness earlier than expected, illuminating the young universe one glowing bubble at a time. Astrobiologists were especially captivated by this revelation. A chiral bias in cosmic formation processes could suggest that the building blocks of life, amino acids, sugars, and nucleotides, may have originated from a universal preference for one molecular orientation over another. If true, this would mean that life's chemistry is not simply the result of chance, but may be woven into the very structure of the cosmos from its earliest moments. Webb's data hinting at such a bias on a galactic scale could carry profound implications for how common and how similar life might be across the universe. While much of the discussion has stayed anchored in hard evidence, these discoveries have also inspired bold theoretical questions. Some scientists have wondered whether what Webb observed is not just a distant galaxy, but a perspective-driven phenomenon shaped by our location in the universe. Could the apparent anomalies arise from the way space-time itself bends and expands around us, creating observational effects that look extraordinary when viewed across immense distances? This line of thought, rooted in anthropic reasoning, raises the possibility that the constants and laws we treat as universal may instead be local expressions of deeper, but context-dependent physics. The implications stretch far beyond astronomy. Webb's discoveries touch the very foundations of physics, cosmology, and our understanding of existence itself. Mature galaxies appearing impossibly early, unusual chemical fingerprints, and concentrated gravitational effects all converge on a single message: the universe is more intricate, more dynamic, and far more layered than our current models can fully explain. And yet, perhaps the most exciting part is that this is just the beginning. Webb has only been operating for a short time, and already it is reshaping our cosmic narrative. As it peers further into the depths of space and the earliest epochs of time, new revelations are almost certain to follow. We may be standing on the threshold of a paradigm shift as profound as the discovery that the universe is expanding. The James Webb Space Telescope has shown us that the cosmos is full of wonders, and that our journey of discovery has only just begun. These encounters encourage us to stay curious, to keep questioning, and to embrace the unknown as part of the adventure. So what do you think? Are we witnessing the beginning of a fundamental transformation in our understanding of the universe? Share your thoughts in the comments, and don't forget to subscribe for more awe-inspiring explorations of space. The universe is vast, mysterious, and endlessly fascinating, and together, we'll keep uncovering its secrets. Thanks for being with us. Leave a comment, like to show your support, and remember to hit that subscribe button for more exciting videos. See you next time.